My name is Jong-Yeol Yang from Professor Jinung Kim's group. I'm gonna introduce my research field and the strategy of my research. After that, I'll explain the research. First, high interface emergen HIPE contain an interface over 74 volume%, and their closely packed drumlets form polygonal shapes. Owing to this jamming emergent phase, HIPE commonly exhibit a solid-like rheological behavior. Moreover, the HIP phase is viscoelastic, and consequently the dislocation of drumlets is structurally hindered, which renders the observance of either sedimentation or creaming very rare. The development of an HIPE system with ultimate stability will significantly broaden the application scope of solid emergence with a rich internal phase. However, actual HIPE are somewhat dynamically unstable because an emergent system composed of two immiscible liquids spontaneously separates owing to the high Gibbs-free energy. Phase breakup is inevitable when the dispersed phase content is higher than 50 volume%. Therefore, a large amount of surfactants are necessary for lowering the Gibbs-free energy in the composition in which the dispersed phase exceeds the continuous phase. Armoring the dispersed phase with solid colloidal particles with sufficient adhesion to the interface, the so-called Pickering emergen, enable the fabrication of stable HIPE. However, in this case, the additional processing of solid particles via sintering or Jolgal reaction and polymerization is indispensable for making a colloidal interface more rigid, which again makes the release of the internal active phase out of such a robust colloidal shell challenging. With this intrinsic problem, this study designed a new type of BCNF dic-18 surfactant with a sufficient number of negative charge on each surface to repel each other elastically. In addition, alkyl chains that can exert strong adhesion to oil drops are covalently bonded to the cellulose unit on the surface of the nanofiber. We expected the hydrophobically modified BCNF dic-18 surfactant to form a resilient monolayer at the OW interface. If the initial BCNF dic-18 stabilized interface is maintained, even in such a jammed state, it is possible to develop a HIPE system with substantial stability. The typical synthetic procedure proposed, BCNF dic-18 was fabricated by modifying the two hydroxyl groups at the C2 and C3 position of the cellulose unit ring with aldehyde groups, generating BCNF dialdehyde cellulose, and consequently grafting octadecyl amines on the aldehyde groups through the Schick-based reaction, finally producing the hydrophobically dialkyl chain modified BCNF dic-18. The successful synthesis of BCNF dic-18 was verified by FTIR analysis. The zeta potential measurements revealed the tempo oxidation and grafting of alkyl chains did not affect the surface charge of the BCNF dic-18 in the range of -45 mV. This result suggests that the carboxylate ion groups at the C6 position of the cellulose unit rings are preserved during the grafting reaction. Unlike the existing surfactant system, BCNF dic-18 achieved an unprecedented stable HIP system. Such promising HIPE stabilization behavior is clearly determined by the structural stability of nanofiber membrane formed by BCNF C18 at the OW interface. Hence, interdrop fusion would never occur even in an environment where oil drops are jammed and deformed. To experimentally confirm this assumption, the mechanical properties of the interfacial BCNF-C18 membranes were analyzed using interfacial rheology measurement. We could figure out that it was clear that the grafting of the C18 arched chains aid the interfacial orientation of BCNF-C18 at the interface, thereby increasing the interfacial storage modulus. However, it was not able to observe that the BCNF-C18 introduced with the 0.36 mmol per gram octadecimal amines substantially maximized the interfacial storage modulus by 2 orders to magnitude. This is because the BCNF-C18 grafted with high contents of arched chains formed a gel phase in the continuous phase, which hindered the interfacial absorption of BCNF-C18. These unique interfacial rheological results suggest that the surface density of the di-arched chains configuration at the cellulose units determine the most effective interfibrillary association between BCNF-C18 membranes. More importantly, this is the condition for obtaining the maximum interfacial elastic modulus of the BCNF-C18 membrane. The barrier performance of BCNF-C18 membrane across the interface was further investigated by observing whether the HIP phase mixing through drumnet to drumnet merging occurred in the state in which the HIP drumnets are closely packed with each other. To demonstrate this visually, two sets of OWHIPE in which the oil phase was labeled with Nile lead and vinyl anthracene were prepared. Thus, only the oil drumnets were labeled with different fluorescent probe. However, these were the same HIPE. Because HIPE are solid and their oil drumnets are tens of micrometers in size, if any internal phase mixing occurs, it is obviously due to merging between the drumnets. Upon pressing the two HIPE between the glass, they generated a clear phase boundary. By monitoring the change in the fluorescence intensity of the overlay area across the phase boundary, that in the HIPE prepared using the BCNF-C18 grafted with the C18 arched chains within the 0.36 mmol per gram, insignificant interface drop fusion occurred. However, when the BCNF-C18 grafted with more C18 arched chains was used, the HIP boundary area turned into magenta in 20 minutes, implying that the adjacent oil drops were more readily fused through the BCNF-C18 membrane. This result confirms again the strengthening of the BCNF-C18 membrane significantly contributes toward maintaining a stable HIPE phase. In summary, this study introduced a facile and promising approach for establishing a stable BCNF-C18 armored HIP system. The key technology developed herein is to armor suspended oil drops with a resilient BCNF-dicing-18 membrane, thereby structurally preventing interdrop fusion in an HIPE environment where oil droplets are closely packed and jammed. Thank you.